Good morning, my viewers. Good morning, my friends. Welcome to another video that concerns mathematics. So, this is going to help those who are preparing for their exams and those who are trying to do mathematics all over the world, no matter the school you are going and the program you are following. Let's get started. This video will be talking about what will be the proof of getting the area of a circle, which is pi radius squared. Remember, in some many questions of paper 3 mathematics, you will be required to prove the area of a circle, you will be required to prove the circumference of a circle, or there will be questions that are inclined to asking you to prove that the area of a circle is pi radius squared. And this is what I want to show you. I have come out with 5 simple steps on how you can answer this question. The first one is you are going to make a geometric representation of what you want to prove. Secondly, you are going to make some changes in that particular diagram that you have created. And the third thing is once you make those changes, you are going to find the area of the change you have made. Then you will use your limit concept in order to find a value that is going to be equivalent. There is something else that you need to do to complete the proof for the understanding of those who would not understand step 4. And we are going to use the Maclaurin series formula to complete the proof. But from step 4, those who are versed in mathematics will understand what is it and they can end there. But those who will still not understand how we get the value of a specific expression, the next step, step 5, is going to help you to understand that. And note that at the bottom of the screen, you are going to see the Maclaurin series formula. The first step says you need to make a geometrical representation. This is valid for any question that concerns geometry, trigonometry, functions. Most of the questions. It's always important for you to see the big picture of what is happening in that specific scenario before you start the question. What I'm going to do here is I'm going to draw a circle with a center, and then I'm going to inscribe a regular hexagon. So I'm using the principle, the Archimedes principle, in order to come out with the area of a circle. So I'm going to use a regular polygon, and I will start with a regular hexagon. Note that a regular hexagon is a regular polygon with 6 sides of equal length, or with 6 triangles of equal sizes. So I have my circle. I'm going to inscribe this regular or a hexagon inside. And then for me to find the area of this regular hexagon, I need to divide this hexagon into different triangles. And if I divide it into different triangles, this is going to simplify the task for me. And why am I going to do that? Because if you realize, for me to divide the regular hexagon into different triangles, I am using some straight lines, and these lines move from one edge of the regular hexagon to another edge. And what do you notice? All the edges of the regular hexagon lies on the circumference of the circle. So this simply means from the center to one of the edges of this regular hexagon actually represents the radius of a circle. So this actually makes me to have one constant, which is the radius of the circle. So I am done, I'm okay with that. Now, the next thing I'm going to do is to actually name my different triangles so that I have a specific number. And the third thing I'm going to do is to fit in the angle that is actually enclosed by these two sides. And remember, since we have equal sides and we have equal length from the center to one to each of these edges, we know that these angles are going to be equal because also the sides are equal and these lines are also equal. So these angles are equal. Now, the angle of a circle is 2 pi. 2 pi means 360 degrees. If I have 6 sides, this means I'm going to divide all this angle by 6 in order to have the angle of one of the triangle. So this angle is going to be 2 pi over 6. Now I have a clear picture of what I'm looking at. I can easily find the area of this regular hexagon. So the area of this regular hexagon will be equal to the number of triangles created by this hexagon multiplied by the area of one of the triangles. Now, how do I look for the area of this triangle? I'm going to use the geometric formula for the area of a triangle. What is that geometric formula? The geometric formula says that if you have a triangle of sides A, B, and C with angles A, B, and C, which is equal to theta, then the area of this triangle is equal to half the product of two of the sides multiplied by the sine of the angle created by these two sides. So if you look here, the area is equal to half AB multiplied by sine theta or AC multiplied by sine B. So that's exactly what it means. And in this case, we are going to use theta, so we have half AB sine theta. Now, if you come here, what do you see? If you consider this side as A, this as B, and this is theta, so our area of T1 is going to be half r times r multiplied by sine 2 pi over 6. So this is what we are going to have. Now, to get the area of the regular hexagon, we are going to multiply this area by 6 sides, and this is what we are going to have. So it's going to give us A sub h or A index h is going to be 6 divided by 2 multiplied by r squared sine 2 pi over 6. Remember, in this case, we have only the area of the hexagon, but not the area of the circle, because we still have some spaces that are left out. Let's go to the next point where we are going to change the number of triangles that we have created using. In this case, this regular polygon is going to be divided into n triangles. In this case, we assume that we have n sides that forms n triangles from T1 to Tn. So we have actually changed the hexagon into a regular polygon of n triangles. And now we want to find the area of this regular polygon with n sides. Remember, when we were dealing with the regular hexagon with 6 sides, our area A index h was 6 multiplied by half r squared sine pi 2 pi over 6. So we are just replacing n by 6 or 6 by n, because in this case the 6 sides becomes n sides. So if you replace 6 by n, you are going to have the area of a regular polygon, which is A sub p, will be equal to n over 2 multiplied by r squared sine 2 pi over n. That is very clear to everybody. So now we have the area of a regular polygon with n triangles or n sides. Again, we have not actually gotten the area of the circle because we still have some areas that are left out. For us to get the area of the regular polygon to be exactly equal to the area or approaching the area of a circle, we need to divide the regular polygon into an infinite number of triangles. The sides that are opposite to this angle will be approaching zero, and they will be approaching the line, the circumference of the circle. Then the angle formed by these two lines will be approaching zero, and the number of triangles is going to increase, will be approaching infinity. So this simply means n will be approaching infinity because n represents the number of triangles we are going to create. Again, it is always important to come out with a big picture for you to understand what is going on. And look at the big picture here. If you look at this diagram, you discover that you are increasing the number of triangles or the number of sides for on this regular polygon. So when you increase the triangle, you discover that the angle theta decreases. The sides that are opposite to the angle also decreases. And you see that the number of triangles it increases, and these opposite sides are actually approaching to the circumference of the circle itself. When you infinitely increase the number of triangles from that regular hexagon, the side opposite to theta will be turning towards the circumference of the circle, and the angle will be actually approaching zero. And we are going to use these informations and the concept of limit in order to find the area of this regular polygon with an infinite number of triangles. And if we are able to get this area, since the polygon is approaching a circle, then that formula will actually, the answer to that area will actually be the area of a circle. How do we do that? Let's look at the mathematical representation of what we have just explained. We have now the area of the regular polygon with an infinite number of triangles will be equal to what? This will be equal to the limit as n tends to infinity, because at this point you discover that you have an infinite number of triangles. So this means we are looking at, since we cannot reach infinity, so we will be looking at the limit as n is approaching infinity of the area of that regular polygon with n sides. So what do? We use the limit concept. And this is what you are going to have as the mathematical representation of what we explained previously. What I have done is that I have actually distributed the expression such that the variables should be at the same side and the constants, because our radius is actually a constant. I'm going to distribute this by assembling the constant at one end, and we know our n is our independent variable because it changes. We can change n. And that is why you see here, I mentioned that r of squared over 2 is going to represent the constant. Now, since this is a constant, the limit concept is not going to be applied to a constant. So we can actually shift the constant outside of the limit operation. And our expression will become a index p will be equal to r squared over 2 multiplied by the limit as n tends to infinity of this expression. At this stage, you discover that it is difficult for you to play with this expression and maybe manipulate to have an expression that is going to give you a proper expression to simplify. If you substitute infinity directly into this expression, you are going to have zero. So this is not really defined. What you have to do is you need to use a technique of substitution in this case in order to simplify this. I will take x to represent 2 pi over n. And if I get such that my n will become the subject of that formula. So if you see this from this n, if n is tending towards infinity, x is going to tend towards 0. Like what I told you, if n is increasing from what I explained previously, that angle theta will be tending towards 0. Now, from this case, we can actually simplify this expression. And what will this expression become? This will be r squared over 2 multiplied by the limit as n tends to infinity of 2 pi over x, because 2 pi over x represents n in this case, and we have sine x. Now, if you look here, we discover that 2 pi is also a constant. So that constant can be moved out of the limit operation, and we are going to have the new expression. A index P is going to be 2 pi radius squared over 2 multiplied by the limit of 1 over x sine x, which is just equal to 2 pi r squared over 2 multiplied by the limit of sine x over x. Now, at this point, you actually see the end of the tunnel, because if you look at this constant, you will discover that, okay, there are some parameters that will disappear or some numbers that will disappear, and we start having pi r squared here. But how do we make this expression to disappear? At this point, those who actually understand that the limit as x tends to infinity of sine x over x is equal to 1, they can actually do that, and they will go and have the end of the proof of the area of a circle. But at this stage, we still need to show mathematically how this guy is going to be equal to 1. You can use a graphical representation. You can use your graphical display calculator, and you fit in this expression is going to give you 1. But I'm going to do an analytical method which will actually let you understand how to simplify this expression. And for me to do that analytical method, I need to use the Maclaurin series formula. And that is step 5, where I said use the Maclaurin series formula to complete the proof. Now, the Maclaurin series formula states that if you have a function f of x, that function can actually be expressed as the sum of a particular sequence or series. If you look here, at each time you increase, you are differentiating the function at that particular time, and then you substitute 0 in that derivative. In the first term, you have f of 0. The second term, you are going to differentiate the function once and you fit in. So this is the Maclaurin's series formula, right up to the point where you have n, which means the end of the series itself. You identify that from the second term, you are taking 1 factorial. And when you take 1 factorial as the denominator, it means you are differentiating that function once and you substitute 0. The independent variable is being raised to the power 1. So you start see from here, you differentiate the function once, the denominator is 1 factorial, and the power of the independent variable is 1. So you move forward, and the next term, you are going to differentiate the function twice, and the denominator will be 2 factorial, and the power of the independent variable will be 2. So you just need to understand that pattern, and you are going to create the Maclaurin series formula for any function, and you can actually use the Maclaurin series formula to expand any of the function that you have. Now, using this formula and taking into consideration that we have a function sine x over x. So this function is like a partial function where you have g of x over h of x. So I will take first of all the first one, which is sine x. And if we use the Maclaurin's series formula of sine x, what do we have? If you substitute 0 here, you are going sine 0 will give you 0. Now, if you differentiate sine x, you are going to have cos x. And if you substitute 0 into cos x, you are going to have 1, because cos 0 is equal to 1. Now you have 1 factorial. So that is why at this point you have x over 1 factorial multiplied by 1, and this gives you x over 1 factorial. Now at this point the derivative of sine x is cos x. If you derive cos x, it means you are deriving sine x 2 times. So if you derive cos x, you are going to have negative sine x. And if you substitute 0, you are going to have 0. And you multiply 0 by this expression will give you 0, because 0 multiplied by anything will give you 0. That is why the third term is going to be 0. Now you move forward. If you differentiate sine x 3 times, it simply means that you are differentiating the derivative of the first derivative. We are going to have cos x. And when you substitute 0, cos x is equal to 1. 1 multiplied by this expression, you are going to have x cubed over 3 factorial. You continue until the last term, and you apply the same pattern by differentiating the value you have. That could give you maybe cos theta, and you multiply, you substitute 0 and it's going to give you 1, then you multiply by the coefficient of that particular term, or you multiply by the expression you have at that particular term, and you are going to have x raised to the power 2n plus 1 over 2n plus 1 factorial. To simplify this expression by removing all the terms that are equal to 0, you are going to have this expression, which will be x minus x cubed over 3 factorial plus right up to the last term. At this point, remember that we sine x over x. So I'm going to look at sine x over x. If you divide this expression, if you divide sine x by x, it means you are dividing each and every term in this expression by x. If I divide this expression by x, I'm going to have 1. If I divide this expression by x, I'm going to have x squared over 3 factorial. And this continues up to the last term, where if I divide this one by x, I'm going to reduce the power by 1. And here I'll have x raised to the power 2n over 2n plus 1 factorial, which will be equal to 2 pi r squared divided by 2 multiplied by the limit of sine x over x as n tends to infinity. Here we have to put in the constant outside, and we have here this will be equal to 2 pi r squared over 2 multiplied by the limit as n tends to infinity of this expression, because we replace sine x over x by this expression. That will help us to get the appropriate limit of sine x over x. And this is the proof of how the limit of sine x over x when x is tending towards 0 gives you 1. Now remember, in this case we are talking about when x is tending towards 0. I will take you back. We have x is equal to 2 pi over n. If n is tending towards infinity, then x will be tending towards 0. That is why this expression, the limit when n is tending towards infinity, simply means the limit when x is tending towards 0. And when x is tending towards 0, what do? You substitute 0 everywhere you see x in this function, in this expression. And when you do that, the whole of this term from x squared over 3 factorial right up to the last term is going to tend towards 0. And we will be left only with the constant 1. And the limit of a constant does not change that constant. So the limit of 1 as n tends to infinity, or as x tends to 0, is still equal to 1. At this stage, the whole of this expression tends to 1, like in the previous slide. Then we are left with 2 pi r squared over 2. You discover that we have 2 at the numerator and 2 at the denominator, so they are going to cancel out, and our final expression will be pi r squared, which is actually the area of a circle that is required. So we have come to the end of our proof. Quite easily done. Thank you very much for watching. Please make sure you subscribe to share this video with your friends so that it's going to help those who are actually inclined to mathematics. Thank you very much for watching.